Welcome, everybody. I'm AAS Press Officer Rick Fienberg, and I'm excited to kick off the 237th meeting of the American Astronomical Society with our first press conference. The topic today is news from the dark side. Before I go any further, I want to introduce my assistants today. Susanna Kohler is with us. She's the editor of AAS Nova. Dharani Konchadi is the AAS media intern. Susanna is going to be monitoring the questions. Dharani is going to monitor the Slack channel. And we also have Haley Wall, who's an Astrobytes author, who's the media intern for the meeting and is going to be helping us throughout the week as well. I'll introduce the speakers in a moment. I just wanted to give a couple of quick ground rules. The way these briefings work is that I will introduce the topic and the speakers. They'll all present one after the other, and then we'll have the questions at the end. There's a Q&A button at the bottom of your Zoom screen. That's where we want you to enter your questions. We want you to type them in. And it'd be helpful, your name should be visible already, but it'd be helpful if you would enter your affiliation and, if possible, identify which of the speakers your question is addressed to, though, you know, sometimes it's obvious, sometimes it's not. The Slack channel, which if you haven't joined it yet for press conferences, starts with 000 to make it easy to find, is for you to basically chat among yourselves, say hello to your friends, etc. But we prefer that you actually use the Q&A box in Zoom to enter your questions, because our goal is to read the questions aloud so that they can be recorded into the YouTube video and audible to the people who are watching the live stream on YouTube, and then they'll be answered that way as well. There is no Zoom chat for regular attendees. There will be a few press releases going out today. Now, as you know, the AAS press office doesn't forward them anymore, but we will be posting headlines and links on the AAS homepage under Astronomy in the News, and we'll also be tweeting them via our AAS_press account. And I'll be updating the online press kit with links to the press releases, as well as links to the presentation slides once I've received them from all the presenters. I've asked the presenters not to answer questions in the Q&A box by text. So don't feel ignored if you type a question. We'll get to it during the Q&A period. And I think that is, oh yeah, one other thing is that you have the ability to upvote questions. So if somebody puts in a question and you really like that and want to hear it get answered, you can upvote the question. That'll raise it in the queue. All right, I think that's everything. So again, this topic this morning, or it's afternoon here on the East Coast anyway, is news from the dark side. We're going to be learning some new things about parts of the universe that are invisible. Whether they're objects that we can't see or whether they're phenomena that we have not yet detected. We have 4 panelists. The first will be Jessica Doppel from the University of California, Riverside. She'll be speaking on globular clusters as tracers of the dark matter content in dwarf galaxies. She'll be followed by Sukanya Chakrabarti, who's currently at the Institute for Advanced Study, but is based at the Rochester Institute of Technology. Sukanya is going to present measurements of pulsar acceleration, reveal Milky Way's dark side. Then we'll go to Joseph Simon from the University of Colorado at Boulder. Joseph's going to talk on searching for the gravitational wave background in 12.5 years of NANOGrav data. If you were just at the first plenary, the Fred Kavli plenary lecture by Paul Demarest, you heard a lot of good background on NANOGrav. So that would be useful background. And then finally, Mattia Di Mauro from the National Institute for Nuclear Physics in Torino, Italy, will present interpretations of the Fermi-LAT Galactic Center gamma ray excess. I do want to remind everybody that we are recording this session, so if that's a problem for you, you might want to get out while you can. We are also live streaming to YouTube, and presumably by the end of the day or this evening, my time, we'll have the YouTube video archived on the YouTube AAS Press Office YouTube channel. All right, so with that, I'm going to mute myself and turn it over to our first speaker, Jessica.
Thanks, Rick. Let me go ahead and share my screen here.
Okay, you're good to go.
Awesome, awesome. Okay, so hi everyone. I am Jess Doppel. I am a fourth-year graduate student at the University of California, Riverside, and I'd like to present some of my recent findings on globular clusters as tracers of dark matter, particularly that of dwarf galaxies. So before I jump into the results, I'd like to give a little bit of background. Globular clusters are utterly ubiquitous in the universe. Nearly every galaxy across a huge range of masses hosts a system of globular clusters. And while globular clusters are quite observationally well studied, they prove quite difficult to simulate. And in order to carry out this type of work, we need simulations with both globular clusters and a dark matter component. So we've turned to the Illustris simulation to do this. We've used a post-processing model to tag globular clusters onto existing particles within the simulation. And we do this for the 9 most massive galaxy clusters within Illustris, those with masses similar to Virgo. These globular clusters are tagged at their host galaxies in fall time, and since the simulation has already completed, we can simply trace the globular cluster particles to redshift 0, thus giving us predictions of the locations and kinematics of these globular clusters at present. And here in this image, we show such a map of predicted globular cluster positions for the most massive galaxy cluster in Illustris. Red metal-rich and blue metal-poor globular clusters are plotted in red and blue dots, respectively, on top of the stellar component in grayscale. And while this model does predict an intracluster component, these little dots here, this work focuses mostly on the globular clusters that are associated to the individual satellite galaxies of these galaxy clusters. While we follow the globular clusters of galaxies over a wide range of masses, an interesting question is posed by the globular cluster systems of ultra-diffuse galaxies, such as DF2, which is shown in this lovely HST image here, and also DF4. Their globular cluster systems have very low velocity dispersions, which suggests the presence of little, if any, dark matter, contributing to the potential that these globular clusters reside in. Within the lambda CDM framework, however, dwarf galaxies are predicted to be dominated by their dark matter component. Thus, at first glance, these seemingly dark matter-free galaxies seem to pose a challenge to lambda CDM. And given this challenge, we turn to our tag globular clusters within the Illustris simulation to see what we can figure out about them. So we've made mock observations using our tagged globular clusters, and we find that they fit well within the context of observations. Particularly here is shown the globular cluster count versus their host galaxy's stellar mass. There's quite a bit of overlap in the relation here between our simulated points and observations, shown in the purple pentagons and green stars, at the low mass end, where we find dwarf galaxies. These tagged globular clusters are also able to reproduce the scatter in these observations quite well. And we find that the scatter in the simulated system is in part related to the amount of dark matter stripping that the globular clusters host galaxies have undergone. We have also performed mock observations of the velocity dispersions of these tagged globular cluster systems using an MCMC method. These mock observations show good agreement with actual globular cluster systems, such as those from the SLUG survey, which are shown here in these open circles, as well as classical dwarfs from Virgo in these open triangles, and several UDGs shown here in the colored shapes. And for these UDGs, of course, this overlaps with the very lowest stellar mass galaxies that we can reliably trace with Illustris. Now we've traced these host galaxies back to their infall time to see how their dark matter content has changed since infalling into their host galaxy cluster. And we find that at fixed stellar mass, galaxies whose globular cluster system have lower velocity dispersions tend to have experienced more tidal stripping than those with higher velocity dispersions. More quantitatively, those galaxies whose globular cluster systems have velocity dispersions 1 sigma or more below the median shown in the cyan points have lost a median of about 83% of their dark matter content since infall, compared to 64% for galaxies within 1 sigma of the median. These results suggest that for galaxies with globular cluster velocity dispersions well below the median, and well below those predicted by the simulation, tidal stripping may be a culprit for these low velocity dispersions. And in fact, we find that the velocity dispersions of seemingly dark matter-free galaxies like DF2 and DF4 seem to exist within this regime. So we isolated the dwarf galaxies within the simulation that have similar stellar masses at redshift 0 to that of DF2, or a few times 10 to the 8 solar masses. These stellar mass analogs tend to also have similar globular cluster counts to DF2, and several are consistent with the upper end of globular cluster velocity dispersions for DF2, which are shown here in these horizontal colored bands. We trace these DF2 analogs back in time, and we find that the progenitors of these analogs reside within halos with virial masses between 10 to the 10 and about 3 times 10 to the 11 solar masses. Otherwise, normal dwarf halos, on par with the mass of the LMC for some of these higher end estimates. However, by redshift 0, we find that these analogs have lost more than 90% of their infall dark matter content. This further suggests tidal stripping as a possible formation channel for ultra-diffuse galaxies. And in fact, observational signs of tidal stripping have recently been found for DF4. So perhaps these seemingly dark matter-free galaxies can indeed be formed within a lambda CDM scenario, and don't quite pose quite the challenge that we initially thought. So to recap, we've added globular clusters in post-processing to the illustrious simulation, and we've used these high globular cluster particles to make observations, or mock observations of globular cluster systems within the simulation. And we find that those galaxies with lower velocity dispersion at fixed stellar mass tend to have experienced more tidal stripping than those with higher velocity dispersion. And finally, that ultra-diffuse galaxies with very low globular cluster velocity dispersion may have formed from otherwise normal dwarf halos that have lost a substantial amount of their dark matter content. So thanks for listening. I will turn it over now to Sukanya.
Thank you, Jessica. Hi, I'm Sukanya Chakrabarti, and I'm going to talk about our measurements of pulsar accelerations that we use to derive the galactic parameters that describe our galaxy, including the local dark matter density. And this is the first such derivation of galactic parameters using direct acceleration measurements. Okay. So I'm not able to advance here. Let me stop sharing for a moment. Just going to try this way. Okay, so let me first talk about why we should carry out direct measurements of the galactic acceleration. This is a very, very small number that we're trying to measure. In terms of a change in the velocity, it's a few centimeters per second. So that's roughly the speed of a crawling baby, and not a very fast baby at that. So the traditional method has been to estimate accelerations using observations of the speeds and positions of stars, and that is what astronomers have done now for more than a century. However, the critical assumption here is that, in this estimate, is that the galaxy is in equilibrium. However, I just want to check, are you still able to see my screen?
No, you've stopped the screen sharing.
Okay. Yeah.
Yeah, try one more time. Okay, it's coming back.
Okay.
That'll work.
Let me see if it still lets me advance. Okay. So, however, there is now a number of lines of number of indications that show that our galaxy is out of equilibrium. And the true acceleration in an interacting galaxy may be different than one that is in equilibrium. So let me go through a few examples of this. The image here is from analysis of Gaia data, and it shows the vertical velocities of stars plotted as a function of position. And you see the spiral structure, which has been interpreted to be due to the interaction with the dwarf galaxy. In this image, you see the ripples or corrugations in the disk of the Milky Way. This is from analysis of SDSS data. And again, this has been interpreted to be due to an interaction with a passing dwarf galaxy. In our analysis of Gaia data from last year, we found that the Milky Way had an interaction with the Antlia 2 dwarf galaxy, and you see movies of the interaction here, the stars on the left and the gas response on the right. So there are a number of manifestations of non-equilibrium phenomena in the Milky Way, which is why it's important to do these measurements of the galactic acceleration rather than just estimating them. And improvements in technology now finally make it possible for us to measure these accelerations directly. So over the last year, I've developed two different methods of doing this. One is measuring the change in the velocities of stars over time baselines of a decade using very high precision spectrographs. And what I'll talk about today is pulsar timing. Now, the reason we're using pulsars here, which are very rapidly spinning compact stars, is because they have an extraordinary timekeeping ability. In fact, their temporal stability rivals atomic clocks. So you can see and hear one of them here, and the pulse profile is shown. The ones we use spin even faster than this one. They're called millisecond pulsars. And we use pairs of these pulsars, so binary millisecond pulsars, and what we monitor is the change in the orbital period, which allows us to use them as galactic accelerometers very much in the same way as the accelerometers that you have in your iPhones. So this is a artist's conception of our galaxy. And you can see here the corrugations and ripples in the Milky Way that I just talked about. Superimposed on this is also the tidal debris from the Sagittarius dwarf galaxy as it got too close to our galaxy and was cannibalized in the process. And the sun is shown here. Our sun is shown in the yellow dot, and the inset shows the locations of the 14 binary millisecond pulsars that we analyzed to measure galactic accelerations. And we selected this set of 14 because this is the set that currently have the most precise measurements of the time rate of change of the orbital period. And you can see that there are several that are above and below the galactic plane. So our sun is very close to the galactic plane. There's some that are above and below the galactic plane. And the radial and vertical extent covered by these pulsars is about a kiloparsec or 3,200 light years in the radial and vertical directions. As you know, the radial extent of the Milky Way stellar disk is quite a bit larger than that. However, we can get significant information on the smaller direction in the vertical direction. So these are our results. Given the accelerations that we calculated, we can very straightforwardly determine the galactic midplane density, which is also known as the Oort limit. So this is the total midplane density. I'm giving it here in units of solar masses per parsec cube, but I'll express it in different units in just a moment. So this is the total density, and I can subtract off the baryon or visible matter density to determine the local dark matter density. Now, this is one of the most fundamental parameters that describes the Milky Way. And I've overplotted our value in the left figure here. This is from a review paper. I've overplotted our value on top of other measurements that we have now for more than a century. And you see that this work goes back to the 1920s. And our value of the local dark matter density is lower than other modern estimates, and the error bars are larger. This is a method that's in its infancy, but it is consistent given the error bars with other measurements. Again, the main difference in our work relative to previous works is that we do not make any assumptions of the galaxy being in equilibrium. We were also able to obtain constraints for the shape of the galactic potential, and we found that the pulsars trace the disk shown here in the schematic in the blue rather than the halo. And we find that the slope of the rotation curve has large uncertainties, but is consistent with being flat. The radial coverage of the pulsars currently isn't very large, but that can improve in the future. These parameters inform direct detection experiments for dark matter that are being carried out across the world to try and understand the nature of the dark matter particle. In particular, as you might expect, the rate of these events is proportional to the mass volume density of dark matter that we have calculated here. So let me express it a little bit differently. This average value shown here is in units of grams per centimeter cubed. It's a very, very small number. And if I look at the amount of dark matter within the volume of the Earth, it's less than a kilogram. Okay, so let me summarize. This is using these 14 pulsars. We've calculated the accelerations of stars within our galaxy. And given these accelerations, we've calculated the galactic parameters for the first time. And these parameters inform direct detection experiments for dark matter. We found a galactic midplane density and dark matter density, which are close to, but lower than modern estimates. The shape of the galactic potential traced by these pulsars is closer to that of a disk rather than a halo. There are currently large uncertainties in the slope of the rotation curve, but it is consistent with being flat. And as we get more measurements and combine this method with other methods, we can start to probe dark matter substructure. I will end there and turn it over to Joseph.
All right, thank you so much. Let me go ahead and start sharing my screen. Can everyone see this? I assume. All right. Thank you so much to the entire AAS press office and all of the other sponsors for inviting us here. I'm very excited to talk to you about some new results coming out of the NANOGrav collaboration. My name is Joe Simon. I'm a postdoc at the University of Colorado Boulder, and I'm giving this talk on behalf of our entire collaboration. For those of you who weren't at Paul Demarest's fantastic plenary this morning, NANOGrav stands for the North American Nanohertz Observatory for Gravitational Waves. We are a pulsar timing array, which is a type of gravitational wave observatory. What I'm showing here is a picture of the gravitational wave spectrum. And just like when you're sitting down at a piano, the frequencies that are further to the left are lower, and the frequencies on the right are higher. just like the electromagnetic spectrum, we need different instruments and observatories to observe different parts of the gravitational wave spectrum. I'm sure that we've all heard of the incredible results that have come out of the LIGO, Virgo, and Kagra consortiums, and pulsar timing arrays like NANOGrav are sensitive to gravitational waves from a completely different part of the spectrum. We are complementary experiments, and we are probing the gravitational waves from supermassive black hole binaries. As we just heard from Sukanya, millisecond pulsars are incredible objects, and you can use them to study all kinds of interesting features throughout the galaxy. They are stellar remnant, so after massive stars go supernova, what you're left with is about 1.5 times the mass of the sun, smashed down into about the size of a downtown city, and spinning about as fast as your kitchen blender. And to create a pulsar timing array, we monitor the signals from a large number of these objects, and we actually create a galaxy-sized gravitational wave detector within our own Milky Way. All right, and so, oops, sorry. This video might play or it might not. Sorry, but what one of the things that happens is that here on the Earth, we're actually kind of bobbing in an ocean of low frequency gravitational waves. And as these waves pass, the Earth gets kind of pushed around very slightly, very smallly, in slightly different directions. And as the Earth is pushed closer to a pulsar, the pulses from that object appear to come a little bit sooner than we expect. And as the stretching and squeezing of space-time from these gravitational waves continues to happen and the Earth moves away, then those pulses come a little bit later. It's kind of like a Doppler shift, but not exactly. What this does is that it leaves a specific imprint across all of the pulsars in our array. And so as the Earth is kind of pushed slightly closer to a pulsar in one part of the sky, pulsars on the other part of the sky we are pulled slightly away from. And so the pulses kind of arriving slightly sooner or slightly behind when we expect is correlated depending on where the two pulsars are in the sky. And so we will see the pulsars changing in a slightly different way. And the only thing that we know of that causes this specific pattern is a passing gravitational wave. Today I'm going to be talking about results from our newest data set. It includes over 13 years of observations on 45 pulsars. However, as you'll see here, this shows observations as a function of time. And so we are continually adding new pulsars to our array. And so the baseline of each pulsar is slightly different. We have been using two of the most sensitive radio telescopes in the world, the Green Bank telescope and the Arecibo observatory. As you heard this morning, the science legacy of the Arecibo observatory is really great. And we are incredibly saddened by its loss and the collapse. We're hoping that this data set and the data that we already have in hand will continue as a legacy to this incredible instrument. All right, and so now to what we have found. For the first time, we have actually found a signal in our data. And so here I'm showing a spectrum, again, lower frequencies on your left, higher frequencies on your right. And what we're finding specifically is a low frequency signal that you're seeing here sticking up above our noise floor. And it is a common signal amongst all pulsars in the array. And we are seeing incredibly significant evidence for this signal. This excess kind of low frequency power across the entire array is what we expect the first hints of the gravitational wave background to look like. However, is this the gravitational wave background? Well, unfortunately, we do not have the definitive evidence for the cross-correlated pattern that is indicative of a gravitational wave background and only a gravitational wave background. Now, we don't have evidence for it, but we also don't have evidence against it. And so this data set is kind of stuck in a really interesting spot. We can also use these cross-correlated patterns to search for other kinds of noise processes, and we find strong evidence against them. So here we are. We have this really significant evidence for a common signal. However, we can't quite say what it is yet. We can say what it's not, but without this telltale signature, we cannot say whether or not this is the gravitational wave background. However, we have been doing some simulations, and we have found that if this is actually an astrophysical background that's starting to appear, then future data sets will show increasing evidence for these correlations that are specific to the gravitational wave background. We are currently working with our international partners to verify this signal in other pulsar timing data sets. And with the inclusion of more data and more pulsars, our simulations show that the definitive evidence that we are searching for could emerge within the next few years. I would invite you all to please go to our website if you want some more information, and to also come to our special session on Wednesday, where we will be talking about kind of what the implications of this are and kind of what the coming decade looks like for nanohertz gravitational wave detection. Thank you very much. And with that, I will pass it off to our final speaker. And if I can stop sharing my screen. There we go.
Okay, so today I'm going to talk about the galactic center excess measured by Fermi. I'm Mattia Di Mauro, and I am a researcher of the National Institute of Nuclear Physics. And so the topic covers the data of Fermi. Fermi-LAT is a telescope that measures gamma rays from hundreds of MeV up to almost 1 TeV. And several groups have found an excess of gamma rays in the direction of the galactic center with respect to the gamma emission due to the interstellar emission, point sources, and the Fermi bubbles that are lobes around the galactic center. In this figure, I show the spectrum, so the flux of gamma rays from the galactic center. And the data are these black data points. The blue and the red points are the interstellar emission. The galactic center excess is given by these brown red points. So you see here that it is actually very difficult to find precisely the characteristics and the spectrum of this excess, because its flux is about a few percent level with respect to the data. Regardless, the fact that it's much fainter than the data, several groups have found that this excess is bright, its spectrum is peaked at a few GeV, and is spherically symmetric around the galactic center. The interpretation of the galactic center excess is still a mystery. The cosmic ray electrons and protons injected from the galactic center has been invoked as a possible interpretation, as well as dark matter particle interactions or pulsar located around the bulge of our galaxy. But no previous studies have searched for dark matter consistently from the galactic center region and from other objects that we think are very dense of dark matter, like dwarf galaxies, or in rare cosmic rays. Moreover, the recent evidences that possibly also pulsars can explain the galactic center, these evidences of 2015 has been questioned by recent papers of last year, of 2 years ago and the last year. And finally, cosmic rays cannot explain all the properties of the galactic center excess. Okay, so the solution is really far to be solved, and I tried to start working on this topic 2 years ago, and in these 3 papers, I report here the titles and the journal reference. And in the second paper, I analyzed the data from Fermi to characterize this excess with all the properties. And in the third paper, I and Martin Winkler from Stockholm University, we tried to make a multi-messenger constraint on the dark matter interpretation of the galactic center excess. So first, I will focus on the second paper, where I made the data analysis with 11 years of Fermi data in order to study all the properties of this galactic center excess. So the first property is the spectrum as a function of energy. And this is peaked at a few GeV of energy with a high energy tail that reaches almost 40, 50 GeV. A very important feature of this excess is that its spatial morphology, so basically how the shape of this excess is, does not depend on energy. So this gamma index is basically the slope of this excess, so how it is decreasing with a radial distance from the center. And as you can see, this gamma is basically constant with energy. There is no big change with respect to energy. And this is very important for interpreting this galactic center excess. Finally, the galactic center excess is roughly spherically symmetric around the galactic center. All the properties I'm showing here makes the dark matter interpretation a very interesting and exciting solution. But if you really want to claim that the galactic center excess is due to dark matter, you should try to search for dark matter also in the production of other particles or in other targets promising for gamma rays. This one here is the gamma ray map from dark matter from a simulation. The galactic center is the brightest spot that you predict from dark matter, but also satellites of the galaxy, for example, dwarf galaxies, are very dense of dark matter and promising for a gamma ray detection. On the other hand, you also have cosmic rays, and for example, positrons and antiprotons are very rare cosmic rays, much lower than protons. And the flux of these cosmic rays could hide a dark matter signal. So it's very important to study in different targets and different cosmic particles if you have a signal of dark matter. So first we fitted the galactic center spectrum with the dark matter flux using different channels. So the idea is that dark matter particles annihilate with intermediate channels and then produce gamma rays. If you use a single channel, so dark matter, for example, annihilating into positrons and electrons, or B bar quarks, you can fit roughly well the data around the peak, but you don't explain the data overall in the entire energy range. For example, here, you see that your model is above the data, and here the model, the blue line, is below the data. If you want to find a very good fit to the galactic center excess spectrum, you need a two-channel scenario where dark matter annihilates with some fraction into a couple of particles, another fraction into another couple of particles. In this case, the positron, electrons, and BB bar, or tau plus, tau minus, BB bar, fits pretty well the data. So once we provided all the coupling parameters to fit well the galactic center excess, we tried to make an analysis towards dwarf-spherical galaxies using this paper, making a combined analysis of 48 dwarfs, but we don't find a significant gamma ray flux. And the only thing we could do is put limits, and in particular upper limits, for this parameter, that is the annihilation cross-section. Basically, this is the strength with which dark matter particles annihilate. The upper limits, meaning that it is possible only for configuration that are below these lines. And in fact, you see that the galactic center excess properties, so this green data point or the green band, is not all above these lines, meaning that the non-detection from the dwarf is compatible with the dark matter interpretation of the galactic center excess. Antiprotons cosmic rays have been used in the past to try to find dark matter. AMS has recently released 7 years of data, and we used, together with Martin Winkler, the latest AMS data to try to find if there is a signal of dark matter. So we fitted all the latest AMS data, we searched for dark matter, but we didn't find any significant signal. So as before, for dwarfs, we put upper limits for the annihilation cross-section. In this case, the limits depend on the size, the vertical size of the diffusive halo. So basically, how is the height of the galaxy for the propagation of particles. And we find that most of the candidates for the galactic center excess as dark matter are compatible with the limits for antiprotons only if the vertical size is smaller than 2 kiloparsec. And finally, we search for dark matter in positrons that are another very rare cosmic species. And we use 2 cases. We tested different vertical sizes. And regardless of the size, we find that the candidates for which you have a fraction of annihilation into electrons and positrons, so these orange, gray, or red lines, you see that these upper limits from positrons are below these data points that are the dark matter candidates for the galactic center excess. Meaning that if dark matter annihilates for a portion of its branching ratio into electrons and positrons, the upper limits are below the best fit for dark matter in the galactic center. And so it's ruled out that the dark matter interpretation of the galactic center can go for a portion of its branching ratio into electrons and positrons. All the other channels survive to these upper limits. So to conclude, we find very precisely, or more precisely than before, what are the properties of the galactic center excess. We try to find dark matter also in other targets, for example, dwarf-spherical galaxies, in antiprotons, or in positrons. We don't find any signal in these other targets of cosmic particles, and using the upper limits for the annihilation cross-section from these other targets of particles, we can say what are the good candidates of dark matter and the good properties for the galaxy that makes possible that the galactic center excess is given by dark matter. And in particular, dark matter that annihilates into muon plus and mu plus particles or mixed muon and quark channel is a possible dark matter candidates that explain all this cosmic ray data. Okay, stop here. And I think there is then the question time.
All right, thank you very much. Thanks to all 4 of you. A lot of interesting stuff here. I know we do have quite a few questions queued up. Remember, if you want to type a question, type it into the Q&A box. And Susanna Kohler, editor of AAS Nova, will read the questions in priority order.
Okay, great. The first question that we have here is for Joseph. Will FAST be contributing to this work? FAST, for those of you who don't know, is the 500-meter aperture spherical telescope in China. And the question continues, if so, when and how much more sensitive will it be compared to Arecibo?
Yeah, okay, so NANOGrav is a part of the International Pulsar Timing Array, right? And so this is a collaboration of pulsar timing arrays around the world. And so there are currently collaborations in the US and Europe and Australia. And that should soon be expanding to other telescopes in other countries, which will include FAST in China. And so it's through the International Pulsar Timing Array that FAST will be contributing. In terms of how much more sensitive, so FAST is several times larger than Arecibo, and so it will be able to time pulsars with higher precision. But because the characterization and the detection of the background is happening on a much longer time scale, and we're probing larger time spans, it'll probably take about 5+ years until FAST is contributing to the characterization of the background. But that increase in sensitivity in the shorter time should improve both our ability to time more pulsars, as well as our ability to detect individual sources above the background.
Great, thanks. We've got a question for Jessica from William Waller of the Galactic Inquirer. And this is just a reminder for our question askers to please identify yourself with your affiliation. Thank you. Jessica, do your observations and analyses place any constraints on the formation mechanism of globular clusters, whether they're strip cores of cannibalized dwarf galaxies or instead formed in situ?
Great question. So our model unfortunately does not follow the formation physics of globular clusters. Within the Illustris simulation, the mass resolution simply is not fine enough for us to actually measure these this type of formation physics. It's something that we hope to explore more in the future, but as of right now, it's not something that we're able to track.
Great. Okay, from Monica Young of Sky and Telescope, we've got another question for Joe. Can you explain a bit more about the amplitude of the signal you found? How can we explain what the amplitude means to our readers?
Absolutely, yeah. This is a good question. So, so the amplitude of the background that is being caused by the if it were to be coming from a population of binary supermassive black holes, it would depend on the masses and the kind of mass function of these objects, as well as the number of binaries. In terms of kind of the amplitude that we're seeing in our data, so the low frequency power that we are recovering is kind of showing up as deviations in our pulsar timing of the order of a few hundred nanoseconds. And so these pulsars are spinning, right, with millisecond periods, and we are able to detect changes in the time of arrival over the course of our entire observation at the kind of hundreds of nanosecond level.
Great, thanks. We've got some questions that got moved into the answered category. So I'm going to move over here to a question for Sukanya from Govert Schilling, freelance. How do you distinguish between orbital period changes in binary millisecond pulsars due to the emission of gravitational waves and changes due to galactic acceleration?
Right, that's a really good question. So what we're looking at is in a different frequency range. What Joseph talked about are gravitational waves that are lower frequencies than what we're looking at. So in principle, there should not be a contamination, but this is something that people do worry about in terms of as a potential systematic effect. We used distances from pulsar timing measurements. And in principle, this can be a potential systematic, but people have compared the distances determined from pulsar timing measurements to VLBI measurements and to Gaia measurements in the cases where the pulsars have a white dwarf companion, and found that they are comparable.
And as long as we're talking with you, Sukanya, there was a confirmation question from Leah Crane of New Scientist. Can you confirm again, please, the number of pulsar pairs you used and the spatial extent that they occupy?
Right, we used a total of 14 binary millisecond pulsars, and these pulsars are distributed in radius and vertical height they're within about a kiloparsec of the sun, that's about 3,200 light years. So they give us the most leverage currently. The distribution of these binary millisecond pulsars currently gives us the most leverage in the vertical direction in the smallest dimension. And that's why we were able to get significant constraints in that direction for the Oort limit and the local dark matter density. We also gave values for the slope of the rotation curve, but here the uncertainties are larger because we don't have as much of a leverage in the radial direction.
Great, and then we have one more question for Joe from Monica Young at Sky and Tel. At the plenary this morning, we were told that we might see definitive evidence within a year, while you said a few years. Are you just being more cautious, or are there specific things that need to happen, for instance, a specific number of pulsars or additional data from other observatories that we're waiting for? And does the loss of Arecibo affect this timeline estimate?
So let me start first with a Arecibo piece here. So we were collecting data at Arecibo right up until the first cable failure back in August. So we have our current data set, the 12.5-year one, extends through I believe through the middle of 2017. And so we have Arecibo data in hand through the middle of 2020. And so the timeline in terms of getting this next data set processed and analyzed isn't impacted by the loss of Arecibo. And I think what's happening between Paul and my outlooks is I'm probably being a little bit more cautious, but then there's also a difference between when we are done taking data to when we complete creating the data set to when we are confident analyzing that data set. So there's a bunch of different steps that have to happen. We are in the process of creating our next data set. That should be completed within the next year. We need to then analyze that and do the same kind of statistical cross checks that we've done on this current one, and so that could take a bit more time. So that I think that's probably what's happening in terms of our discrepancies in terms of outlook time.
All right, great. I think that is all of the questions we've got over here in the Q&A.
I have one, and since I'm not able to type into the Q&A as a panelist, I need to ask it aloud. This one's actually for Mattia. So when you look at the data that you've analyzed and you look at the dark matter decay channels that still seem to be permissible, do those available channels argue in any way, pro or con, for whether the dark matter might be weakly interactive massive particles or axions or sterile neutrinos or any of the other candidates that we hear about? In other words, have you argued in favor of one direction versus the other for what the dark matter actually might be?
Yeah, this is a great question. So the candidates that survive to our limits are compatible with weakly interacting massive particles. Now, of course, there are many theories, particle physics theories behind a WIMP, and we are providing the coupling parameters, so the properties of these candidates in our paper. And so in the future, for example, LHC or other particle physics detectors could test these specific candidates because there is always, you have to assume always a particle physics theory when you go from the indirect detection to the LHC or particle physics detection or indirect detection.
Okay, I have a question for Jessica too. You were talking about the dark matter being stripped from these galaxies. Can you explain, first of all, whether that means that ordinary matter is being stripped as well, or if so or if not, how do you tell?
So ordinary matter, we look at the stellar components as well, is indeed being stripped, and in the simulation, it's a lot easier to tell than with observations. Of course, we can simply track via merger trees or even looking at individual snapshot files what these particles are doing. So in particular, when we look at how the matter is stripped, we are comparing directly how much of a mass component a galaxy has in its past versus at the present day.
Okay. All right, I had a couple of other questions, but they've been asked by others, so I'm done too. Tharini, did you see anything come across the Slack channel, any rogue questions?
No, there are no questions in the Slack, so thank you everyone for using the Zoom Q&A box.
Great. Well, that means that we're finishing exactly on time, which is the AAS press officer's dream situation. So thank you all very much for your cooperation. So first of all, I'd like to thank all of our presenters today. Great job. Really nice and interesting results. I'd also like to thank the audience. At one point, we had over 100 people tuned in here and 40 people tuned in on the live stream at YouTube. So that's if we were at an in-person winter meeting, we'd have a pretty full standing room only crowd, which is great. I want to thank the institutional public information officers who have created some press releases to go along with 2 or 3 of these presentations. As I said, I will post those on the AAS website under Astronomy in the News, as well as tweet them via AAS_press. And also I'll post links to them on the press in the online press kit this afternoon. So that's it for this one. Our next press conference is this afternoon at 4:30 p.m. Eastern Time. The topic is exoplanets and brown dwarfs. And if you've been attending AAS meetings in the last decade, you know that that's a topic that is virtually guaranteed to have a press conference at every single meeting. And in fact, there have been times where we've had 2, and I think once we even had 3. So we'll have a look at worlds beyond the solar system this afternoon. So that's it for now. Thanks so much to all of you. Thanks to Susanna and Tharani and Haley for helping me out today. And we'll see you all again this afternoon. Thanks again.